section G5, I want to talk about work and forces for the case where the acceleration is 0. And the sled problem fits this criterion where he talked about pulling the sled at constant velocity. So let's look at this problem again. We have a force at some angle theta. We have a normal force. We have the weight, and we have the friction. So that's what's going on in this problem here. We have the force at some angle theta. We have the mg pulling down. We have the normal force going up. And we're going to have friction opposing us. So there are the four forces. F and little f and mg. F and little f and mg. And I would like to calculate the work on all three. First of all, we'll do F, the pulling force, capital F. The work for the pulling force, here's our definition, force dot with the distance. And here, the answer is going to be F cosine of theta times d. We're finished. 2, the normal force N. Well, the normal force, that's going to be N dot D. And that's going to be the magnitude N. And here we're going to have 90 degrees. So we want the cosine of 90 degrees times D. And since this is 0, there is no work. The normal force doesn't do any work. 3, if we go with the frictional force, then we set it up the same way, F dot D, little f dot D, and here you have little f. You can put the magnitudes down first and then the angle, whatever your preference. This is 180 degrees. Since I'm going to the right and the force is going to the left, is 180 degrees, and that's going to be -1. So that's negative FD. And we really don't need to do the weight, the mg case, because it's going to be 90. Well, we'll do it. So this is due to gravity. That's mg, the g vector, dot d. And that's not, it's going to be, well, technically, it's a -90, but it doesn't matter because it's still going to be 0. So you're pulling down here, it's going to be 90 degrees, but it's a -90 if you're measuring the angles from this way, like this. This is the convention, is to measure the angles counterclockwise. So now if we add up all the works, for the total work, we need to add up all these. So we're going to get F cosine theta times D plus 0 plus a negative little fd plus 0. But because there's no acceleration, F cosine of theta is equal to little f. So that means here, F cosine theta minus little f times d, this is going to be 0. And the net work done is going to be 0, which now makes sense because the change in kinetic energy is 0. It's constant velocity. If you add them all up, you get 0. Now, the mother is doing work. Sure, the mother is doing work, so if you want to know what the mother is doing, you have one of the four things. But so since there's no acceleration, the total work done is 0.